I thought for a while about what to talk about, and in the end, I think I decided to go maybe with the spirit of the conference. So I sort of chose something that will have a little bit to do with calculus of variations, but I think really touches sort of everything in a maybe a tangential way, but at least it does touch everything, I think. But the main focus is symplectic embeddings. So I thought I would start by just reminding you all and reminding myself what a symplectic manifold is. So that is just a smooth manifold of even dimension, equipped with a 2 form. And this 2 form has to be closed and non-degenerate. So the most basic example is if we just take Euclidean space, so R2n or Rn cross itself, with the form being just dx1 wedge dy1, and then plus all the pairs. So dx1 wedge dy1 plus through to dxn wedge dyn. And so locally, at least locally, they all look like this. So it's a good local model, and this is the Darboux theorem. And maybe while I'm at it, just because we are on R2, and there is a little bit of an extra structure here, right? So I could also identify this with Cn, and then I get a complex structure. So again, or in general, an almost complex structure, J. And so the point of an almost complex structure is that this should be compatible if I turn this skew tensor into a symmetric tensor by including the complex structure, then I get some symmetric tensor. And so it's compatible if this is a Riemannian metric. So again, R2n certainly has one just by identifying it with a genuinely complex space. Okay, but the sort of key question in general is to understand the rigidity of the symplectic structure or in other words, to understand, when can you have a symplectomorphism, that is a diffeomorphism, preserving the symplectic structure. Okay. So again, I think these are well known, but again, just as a bit of review for and sort of easy invariant under, right? So if you preserve omega, then certainly you preserve the n-fold wedge product. So certainly you have to preserve omega n, and this essentially is just the volume form. Right, so if you preserve the symplectic structure, certainly you preserve volume. And, well, okay, there's always the danger that maybe it's not any more rigid, right? So maybe symplectomorphisms really are just volume preserving maps. But then there's the well-known result. So there's the there's the quite well-known non-squeezing result. Now, I think usually credited to Gromov, or sort of colorfully termed the symplectic camel. Right, and so what this says is that if I take, let's take the ball of radius 2, let's take the ball of dimension 2n with big radius r. Okay, just in Euclidean space, so again, that's just with this symplectic form, the standard symplectic form. And I want to try and embed it symplectically into so the symplectic cylinder, so that's the two-dimensional ball of radius 1, just cross with r2n minus 2. So sometimes this is written as Z. And so the theorem is if you do have such an embedding, well, you can't embed too big a ball. Right, so here, the radius of the ball has to be less than 1. Right. And so this is something that's certainly not true for volume preserving, right? If I have any big ball that I like, I can always thread the needle. If I only need it to be volume preserving, I can always squeeze it down and eventually get it through. Right, so this is certainly something unique to symplectic maps. And the question, I should have introduced my collaborators, so everything I'll talk about is joint with Kevin Sackle, Antoine Song, and Umut Vorolganesh. So the question we looked at is, how can we quantify this theorem? Okay, in particular, what we asked is how much do we need to remove from the ball? Right, so when the radius is strictly larger than 1, I know I can't embed into the cylinder, but maybe if I take enough out, then I can squeeze it in. And so maybe I should again note that volume let me just write it out. Again, so I'm removing some exceptional set, and then I hope to fit it into the cylinder. And I should note that again, volume is not really a good measure. Okay, so there's a theorem of Kartok which says if we're given a compact set in R2n, then I can actually embed, essentially I can embed X into, I can find an embedding such that the volume of the image of X, sorry, let's write it as 5X, outside the cylinder is less than epsilon. Okay. So I know some part has to escape the cylinder, but that part has as small volume as I like. Right, so volume's not a good, not necessarily a good way, or not an interesting way to quantify it. Okay. Okay, so I thought I would just briefly sketch the proof of non-collapsing, sorry, of non-squeezing. Okay, so the first thing you do is suppose that you have this embedding into the cylinder. And really what I want to do is just compactify this, so we don't want to worry too much about non-compact stuff. We don't want to worry about the boundary of the ball. So I can always fit the ball of radius 1 into symplectically into a sphere of just slightly larger radius. S2. Yeah. Okay, and now this thing S2 cross Tm minus 2 has, so it has a natural complex structure, right? So thinking about S2 as CP1, and then just, again, this guy as complex space. So you have a complex structure, J naught, and a vertical foliation of holomorphic curves. And the area of these is just pi r squared. Okay, on the other hand, if I was able to fit the ball into the cylinder somehow, so just for simplicity, properly contained, then I actually get a push forward, right? So I have a complex structure on this guy just by identifying the ball with its image. So here I have the push forward of the standard structure, and I can interpolate the structure with this one outside of the image. Right. Okay, and so the hard part that I don't want to write down, but I want to emphasize as the hard part, is that you can deform continuously through complex structures this J naught into the one that incorporates the push forward structure. Okay. And when you do that, again, it's a hard theorem, but the foliation deforms along with it. Right, so the upshot is what we get is a foliation. Okay, here it does something weird because the structure has changed. Outside, it's still the same. We still get a J1 interpolates J naught in this guy. And so here we get a J1 holomorphic curves. Again, with area pi r squared. Okay. But I can pull this whole picture back, right? So I can pull this whole picture back to the ball. And so in the ball, I'll have some foliation by now J standard holomorphic curves, so genuinely complex holomorphic curves, right, with everything standard. And on the other hand, okay, so I've mapped these into here, and maybe I don't pick up everything, but still the area is at most pi r squared. Right. So I don't pick up the whole curve. Okay, and so I think at this point, probably most people see the issue. Right, so there are a few different ways to finish the proof now from here. So one way, a really easy way, is to say, okay, you have to have one slice that goes through the origin. Right. So this slice passes through 0. On the other hand, it's holomorphic, so it's a minimal surface. And any minimal surface passing through the origin has area at least the equatorial version. Right, so at least that of the disk. So the area has to be at least that pi r squared. Okay, and so now just by playing these two off each other, you have your bound. Right. Okay. Cool. So that's a very quick and dirty way of doing it. Let me, I guess board talks go a little slower than we're used to on Zoom now. So in the interest of time, let me, I was going to talk about widths very briefly, but let me at least get the theorem up, and then I'll come back and talk about widths. So the theorem that we proved is that if right, so I've taken out a set and I'm able to embed it in, then so we work with n equals 2. So I take a set out of B4, and I'm able to symplectically embed it in. Then the Minkowski dimension, so the Minkowski dimension of the set I take out has to be at least 2. So it has to be big enough in this sense. And actually, we also get a bound on the content. And we have a partial converse. So conversely, B4 of root 2 minus the equatorial B2, I guess also radius root 2, this does symplectically embed into the cylinder. So consequently, it works for smaller r as well. I think it was sort of alerted. We were alerted after we posted this that it works for some higher r, but we still don't know whether it works for all r or if there's a threshold. So there's some interesting problems here. Okay. So that's the theorem. And let me just mention width in a couple of minutes. So I mentioned taking the 0 slice, the slice through 0 is a convenient way to finish the proof. But there are many other ways to finish the proof. In particular, you can deal with the width, right? So the width is essentially the least maximal slice on such a foliation. So I will be very, very loose with the terminology here. But if you, so a width is essentially a bound for any foliation, and you take the maximal slice. If you have a lower bound for that, that's a width inequality. And typically, they don't depend on any structure at all. So let me show you the waste inequality of Gromov. Okay, so you take the foliation in this way. Then there is some slice, some fiber, such that the volume of the tubular neighborhood is at least the same construction, but for the equatorial SK. Okay, so I'll just say it, but if you take t to 0, then again you get a bound for the Minkowski content, right, the K Minkowski content. And there are lots of other versions. So Akopian and Karasev proved a waste inequality like this, where you can replace the sphere with the ball. And so consequently this one as well, just with the equatorial ball. That's the waste inequality we end up using. I should say also Gromov did the same thing, so you can replace Sn with Euclidean space with the Gaussian measure, which is something that has been discussed a lot at this conference. Okay, and maybe let me close with a little piece of information and also a question. So this last one, again, it concerns these foliations by surfaces which have no assumption on what the surface actually is. And Klartag actually has a nice paper where he proves a waste inequality of a very similar form as Gromov said for the Gauss measure, but on Cn, where this map, right, the foliation map, the parameterization is not just continuous, but actually holomorphic. And then he gets a stronger result. And it's kind of curious because in this situation, we have something in between, right? Even in this argument, we only use that one slice was holomorphic. And if you use the waste, you don't use that any of them are holomorphic. But you have that all of them are holomorphic. But on the other hand, maybe you don't have that the total map is itself holomorphic. So there's something curious in between. And so I have lots of questions to pose, but maybe I'll pose that one if there are some applications or some maybe stronger waste inequalities for things that are somehow in between. Okay, so I think I'm way over time, so I'll stop there.